Hello everybody. Today is the last lecture and we will start it with consideration of distribution of electrons by energy levels of an atom. And we already know that there are energy levels in which electrons can occupy in an atom, and the energy of electron depends on mainly on the n number of electron, but also by L in some extent. And it is it is a good guess that, as we know from classical mechanics, that all particles tends to occupy the state with the lowest possible energy. So we can expect that all electrons should be in the state with n equal to 1 and L equal to 0 in atom, but such is not the case. And there is some principle which is called Pauli principle. What is Pauli principle? Pauli is his name. So Pauli principle. Pauli principle states that if we consider particles a system, quantum system, with particles which have spin which is not integer, but it is half integer. So in such a system, there could not be two particles which occupy the same state. We remember that state means that this particle has some particular wave function, and this Pauli principle states that there could not be two particles in the same quantum system which have the same wave function. So wave function, now we consider wave function in atom, and we know that it depends on main number n and azimuthal number L, and also at magnetic number m. And now we know that it also depends on the orientation of spin, so on projection of spin, this is ml and this is ms. This is projection of orbital momentum, and this is projection of spin momentum. So there are totally four numbers which define the psi function and consequently the state of electron in atom. So the principle states that there should not be two electrons with the same set of these numbers. We know that n can be 1, 2, 3, etc. L can be 0, 1, 2, up to n minus 1. ML, projection of this quantum number, characterized projection of momentum on some axis, and it is minus L plus 1, and so on, minus 1, 0, plus 1, and so on, up to L. And finally, this projection MS can have only two numbers, as this is plus 1/2 and minus 1/2. Now, if we look at the fundamental state or ground state of atom, it is also, as in classical mechanics, the particle the particles should occupy the state with the lowest energy, but provided that this state has vacancies. This means that there are no other particles which already occupy this state. And we know that when we considered degenerate states, we derived a value of degeneracy, and we know that it was calculated as sum over L from 1 to n minus 1. This means a number of L's which can L can take these numbers, and for each of these numbers there are 2L plus 1 mLs. So we summarize this 2L plus 1, and this gave us n squared. And for each of these states there are two possibilities for ms, plus and minus 1/2. So total number of states which are different for given n is 2n squares. From this it follows then if we have n equal to 1, then this number corresponds only to 2 electrons. Only 2 electrons can have this number. So the state with n equal to 1 can be occupied only by 2 electrons. If n is equal to, there could be 8 electrons which can populate such a state. For n equal to 3, corresponding, if we use this formula, corresponding number of electrons is 18, and for n equal to 4, corresponding number of electrons is 32, and so on. You understand that if we have n equal to 1, then L is equal to 0, the only possibility. ML is equal to 0 as well. So we have only two possibilities to populate the state, 2 electrons with different projections of ms. Now we have to make a definition that a set of electrons which have the same n and L's, they create a subshell. So this is a subshell. Subshell is a set of electrons which have the same n and L. And all set of all subshells with the same n's creates a shell. This corresponds to shell. Shells are notated by some letters. So if we have n equal to 1, then a shell is called a K shell. K is, this is capital K. If n is equal to 2, this shell is notated by L, 3 M, 4 N, and so on. So next 5 is O. This is a name of shell which corresponds to this N. Now let's create a table in which we will put the electrons in the states which they can occupy. This will be such a table. where here are in the first cell of this table we will put a shell. Then here we will put corresponding n number. Here we will put L number, ML number, MS number, and here we will notate as subshell. So the first n is 1, and we remember that it is a K shell. So for this case we have only one possibility for L equal to 0, ML equal to 0 as well, and MS can have two different values, and we will depict them with arrows, one arrow up, one arrow down, which corresponds to two different orientation of spin projection MS. Subshell is characterized by corresponding N and L, so subshell here is 1S. So S is corresponds to L equal to 0, and 1 it is this number n. Then we see that K shell is filled, so this is filled, and next is n equal to 2, and this is L shell. In this case we can have also L equal to 0, and ML will be equal to 0 as well, and there will be two electrons with different orientation of spin, and as far as this is 2, so this is subshell to S. S corresponds again to 0L. Now for this subshell is filled, and the next next L is 1, because L can have numbers of 0 and up to n minus 1, so n numbers 1 is 1. And in this case ML can have numbers minus 1, 0 and plus 1. And for each of these numbers there could be two different orientation MS. So these are arrows which depict this two orientation of electrons, and this subshell is 2p, and the shell is filled also. Now next is n equal to 3, and shell is M. Now again here is the same picture, 0, 0 and 2 electrons, and this is 3s subshell. Next subshell is 1, minus 1, 0, plus 1, and there are 2 electrons in each case, and this is 3p. And in the case that L is equal to 2, we have MLs minus 2, minus 1, 0, plus 1, plus 2, and again we have 2 electrons for each of these MLs. And the subshell is 3D. When we have a totally filled shell, there are several subshells in each of shell, and for each of subshells it is specific that total azimuthal and spin moments are zero. This means that for subshell L total, L is zero for filled subshell, and S is zero for filled subshell. For example, if we consider this 3D subshell, so we see that the projection of momentum ml for all electrons, if the subshell is filled, so there are all electrons, so each of electron occupies some state. So there are electron which has ml minus 2, minus 1, 0, 1, and 2. And if we sum up all this projection, so we have ml as a sum of f of mLs. ml belongs to each of electrons, and it is seen that if we sum up all these mLs, we will have 0. So ml is 0. If ml is 0, it corresponds to L is 0, because its projection is 0, it corresponds only case when L is 0. Also, if we summarize all these spins for projections for each of electrons, here are 2 electrons, but they have spins which are directed in different directions, so 0, 0, 0, 0, 0, so total spin is 0 as well. This means that if we have some atom and we are interested in its total orbital or azimuthal momentum and spin s quantum number at L quantum number, we can neglect filled subshells. Now we will consider how this Pauli principle explains a periodicity of the properties of atoms, optical and chemical properties. We will start with Z equal to 1, the system which has only 1 electron, and we will increase that by 1, and we will put electron every time in available position, available place in atom. For hydrogen, we have only 1 electron, and this is 1 s electron. This means that n is equal to 1, L is equal to 0, ml projection is equal to 0, and ms is equal to plus minus 1/2. The fundamental term for which atom is in ground state is, in this case, we know how it defines S 1/2, and here is multiplicity is equal to 2. So here is J, this is L, and this is a term as we know how it is. So here is 2s plus 1, this is J, and this is L. Okay, now this is the term. Next is, okay, here is periodic table. Next element is helium. Helium has 2 electrons, so both can occupy the same position. Okay, let's we will draw such a system that we will depict the system for each of elements. So this is hydrogen, and the fundamental term is 2s1/2, and it has one electron at the level 1s. For helium, here we have two electrons, so there is space, available place in this level for different number of ms. So we can put here two electrons. Then configuration will be 1s, and we will denote these two electrons here by 2. And here are quantum numbers for this case. N is equal to 1, L is equal to 0, ML is equal to 0, and MS again is plus minus 1/2. So if the first electron has plus, so another has minus, and here it can be arbitrary, in this case plus or minus, because it is only one electron. And term for this case is S0, 1. We understand that total S is 0 here, total L is 0, so J is 0, and 2S plus 1 gives us only 1. And next element in periodic table is lithium. So here is lithium. We understand that this two electrons we can put here, and the third electron, so lithium has 3 electrons, so we can put 2 electrons here, but the third electron cannot has no place at this level, so we need to add energy level for this electron, and this is 2s. The smallest energy has s electron, so we will put here 1 electron, and then we will have configuration like 1s 2 electrons and 2s for 1 electron. This is okay. It has in this case it has also, if we look, this is 2s, so we have also a fundamental term as 2s1/2, similar to that one. Next element is beryllium. This is beryllium, and it sorry, here is lithium. So beryllium has 4 electrons, and these 4 electrons can be located in these 2 levels, 1s and 2s. So here is beryllium. Here we can put 2 electrons, and here we can put 2 electrons as well. So this term is S0, 1, like this one. And next is boron. And for boron, we have no possibility to put here additional electron, because okay, here we have configuration 1s2 and 2s2. 2 electrons at state 1s and 2 for 2s. For boron, we have 5 electrons. 4 of them can be located here, and the fifth one we need to add additional level in which we will put this electron, and this will be 2p. So for boron we have configuration that 1s2, 2s2 and 2p. Corresponding term is 2p 1/2. For following 6 elements, we have up to neon. So 1, 2, 3, 4, 5. So from boron to neon, we will completely fill this 2p subshell. Indeed, for 2p subshell, we remember here we have for 2p we have possibility to put 1, 2, 3, 4, 5, 6 electrons. So we started from boron, put only 1 electron. So we have a possibility to put there up to 6 electrons. So for neon, we will have this case when this subshell is completely filled. And so we remember that for this completely filled subshell, L is 0, S is 0, so we can consider next element. And when we consider next element after neon, we can neglect all this momenta for filled subshells. And next element is sodium. In Russian it is natri, so sodium. And for sodium we have a configuration. For sodium we have configuration 1s, 2 electrons, 2s, 2 electrons, 2p, 6 electrons, as we remember, and 3s. So for this 3s state, we have a fundamental term which is 2s 1/2. Look, this term, which we remember that term, determines optical properties of atom. So, and by the way, and chemical properties as well. And look, this term corresponds to term for hydrogen. So the property of sodium resembles that of hydrogen. So it is hydrogen-like atom. And by the way, if we look at this distribution of electrons, we see that this optical electron or valence electron, which is external electron over filled subshell, has n equal to 3. Remember when we drew this picture for energy levels of sodium, we started with n equal to 3 because all inner shells and subshells are occupied by electrons, and there is no place for this optical electron in those numbers which are less than 3, for n numbers less than 3. Well, we have to take into account that sometimes it is possible to put electron at different states because and all of the states do not contradict with Pauli principle. For example, look on boron. We have only 1 electron in state 2p, here, but there are 6 possible positions on which can be occupied by next electron. So if we occupy one position here, one electron in boron, next element after boron is carbon. And then for carbon, we can put electron in each of the empty positions. And the question arises for which position this electron should be put. This is regulated by some empirical rules. And first, let's consider what are this possible orientation. We will consider it in some kind of scheme. I will draw it here. For example, here will be some axis Z. Then we will draw L with projection on this axis. So, and S is projection on this axis. So this is L, this is S, and in this case we have ML equal to 1 and MS equal to minus 1/2, because it is up, it is down. Next we can have L of the same length, but with orientation perpendicular to Z. So this corresponds to ML equal to 0. And again, MS we will use minus 1/2. So it is another state. And next we can have L oriented directed down. So ML is minus 1, and MS will draw again as this is S, this is L, this is S, L. So ML is minus 1 and MS is minus 1/2. Now we can draw the same with, look at these 3 states. We have MS minus 1/2. Now we can use the same states, but with MS plus 1/2. So in this case we will have this is plus L plus S. So this corresponds to, this is 1 plus 1/2. This corresponds to, this is L, this is S. So 0 plus 1/2. And next, this is S, and this is L. So ML is minus 1, and this is plus 1/2. This corresponds to this 6 electrons. This 6 different orientation of spins and MLs. And now we can say that if we have 1 electron, the question arises what should be the state which will be occupied by the second electron. This is regulated, as I already said, by some empirical rules. These empirical rules are Hund's rules. So Hund's okay, this is S, this is Hund's rules. Well, the first rule says that of the terms belonging to a given electron configuration, the term with the greatest possible value of S, capital S, total spin moment, and with the greatest possible value of L, total L, at this L will have the lowest energy. If it has the lowest energy, it is the level which will be occupied, because we remember that each physical system tends to occupy this state with the lowest possible energy. Now let's look, this is the first rule, and let's look at our case. The rule says that we need the greatest possible value of S. So the greatest possible value of S for 2 electrons is S equal to 1. This means that both electrons have S oriented have spin oriented in the same direction. So we can use this 3 states because here are all the same direction, or this 3 states because all this are also oriented in one direction. So it does not matter which of these two we choose, but okay, we have 2 electrons with the same orientation of spin. Now for this maximum S, we need maximum L. So maximum L means that L should be, for this case, should be equal to 1. Look, if we consider this case, so this means that 1 electron has ML in this direction and another has this direction. Then a sum will give us L equal to 1. So we can took 2 electrons, and or we can took 2 electrons, this and that one. Now the question arises how to find J. Before we will find J, again, why L is equal to 1? Because of Pauli principle, we cannot have 2 electrons with the same direction of L. So they have to have different MLs. So we can choose this and that, but then L will be equal to 0 because ML will be equal to 0. And if we choose these 2 electrons or these 2 electrons, we will have maximum L is equal to 1. The second rule of Hund's rule states that the multiplets formed by equivalent electrons are normal. This signifies that the energy of the state grows with increase in J if not more than half of the subshell is filled, and are inverted, the energy diminishes with an increase in J if more than half of the subshell is filled. So what we have a subshell which is filled less than half of this. We have only 2 electrons, and totally we can put there 6 electrons. So we have case when Hund's rule says that this normal means that J should be 0. Indeed, if we sum up these 2 moments to obtain J, we can have 2, 1 and 0. And as far as the Hund's rule says that the energy increases with J, in this case when only less than half of subshell is filled, then we need to take the lowest possible J. Then fundamental term for carbon is 3p0. The last topic which we will consider in atomic physics is X-ray spectra. X-ray spectra are characteristic X-rays which are emitted by atom, characteristic in a sense that they are specific for each of atoms. from which these X-rays are emitted. How this spectra, what is physics, how they are produced? They are produced after some inner electron is knocked out from atom. Imagine that we have some, okay, if we consider again atom in the Bohr's model, so there are some electrons which in the first here in the first shell there are 2 electrons. Next there are 8 electrons. Here many electrons already. Okay, next, and so on. And if we have some electron which is knocked out from, for example, here from this shell, so there is vacancy on the shell, and then electron from the next shell will fill this position, and if it change its energy while this jump from this orbit to this orbit, it will emit some ray. And this ray has energy in the X part of spectrum. This spectra consists of several lines and several series of lines, and this series of lines are notated by the same letters as corresponding shells are notated: K, L, M, N, and so on. And how it looks in an energy scheme. If we have the lowest energy for K shell, next is L shell, next is M shell, N shell, and so on. And if we have some vacancy on this shell, so 1 electron was knocked out, so electron from L will go here and will emit some rays which are called K alpha. And if it is probability, as all things which happens in quantum mechanics, there are some probabilities that this vacancy will be filled with electron from L shell, but also it is possible that it will be filled from M shell, or it will be filled from N shell, and then all this is called K beta, this is K gamma, and all this series is K. Next, you understand that each of such K series should be accompanied by L series, because if, for example, K, this L electron goes here, so there is vacancy now in L. So electrons from M, N, and so on will fill this vacancy. So there will be such transitions, and this is L alpha, this is L beta, L beta, and so on. So this is L series. This is just some, I would say, approximate interpretation, because you understand that each of these lines has a fine structure, because, for example, for L we have different terms. Here it is split in 3 levels also, and 3 subshells also, and there are different possibilities to have 2p 3 halves, 2p 1 half, and 2s 1 half. So this is also for some fine structure which corresponds to this level, and K has term only 1 as 1/2. So this is more complicated structure as compared which is depicted here in this scheme. It is interesting to mention that when we go from low Z numbers to greater Z numbers, the spectra resembles each other as they are only shifted in higher energy end of spectrum because so shorter lines because all these transitions are in the inner between inner shells, levels in the inner shells, and we already saw that all inner shells in atoms are similar, so these spectra are also similar, and the dependence on Z is according to Moseley law, and the Moseley law says that the square root of omega is C Z minus sigma. And here some sigma and C are some constants, and sigma is the same for the same series for all elements. For example, for K, sigma for K, sigma is 1. And for L, sigma is 7.5. It is found empirically. And C has its own value for each of lines, and the same for all the elements. It is easy to understand why this Moseley law works. For example, for K alpha, it was found that C is square root of 3/4 R, where R is a Ribet constant. Then, as far as K alpha for sigma for K alpha is 1, we can say that omega is 3/4 R Z minus 1 squared. Or we can rewrite it as R Z minus 1 squared, and here 1/1 squared minus 1/2 squared. Look at this. It looks like Balmer's formula. This corresponds to some transition from one level to another level. But here is Z minus 1. What is this? Why this term appears? This term appears because this transition occurs not in the field of nucleus, but in the field of nucleus, which is screened by one electron. And so Z belongs to nucleus, and Z minus 1 means that there is one electron which screens this charge of nucleus. And for all other lines, we can write similar, that it is R Z minus this sigma squared, and here 1/1 n squared minus 1/n2 squared. So it again corresponds to the transitions between different levels. This is the fundamental sense of Moseley law.